Well, good evening, folks. Glad you're here. Got a relatively small number of folks here live, but maybe we'll add a few as the time goes on. Hopefully, I had a chance to work on the worksheet that I sent out for the last lecture. And I want to begin today by looking at a couple of those problems, which indeed are going to be problems that will extend our idea of Taylor series. So this really is one of the more important concepts in the course, certainly one of the most important if we're going to do analysis in applied mathematics. So I'm going to take a look at question 2b from the worksheet. Namely, we want to go ahead and look at cos x squared, and then once we do that, find the integral from 0 to 1 of cos x squared. So let's take a look at this. Integral from 0 to 1 of cos x squared dx. And again, we're working with Taylor series, so we need to remember what the Taylor series for cosine x is. But let me remind you of all of the Taylor series we like to remember. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, dot, dot. So x to the k over k factorial, sum as k goes from 0 to infinity. Sine x are the odd powers. So sine x alternating x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. And cosine gives us the even values. So cosine x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus dot, dot, dot. Now you'll notice that this question asks us for cos x squared. So we want to use a Taylor series for cos x squared to then evaluate that integral from 0 to 1. So we're going to replace all of the x's with x squared. So this is going to be the cosine of x squared. So wherever we see an x, we're going to rewrite it with an x squared. And I believe the worksheet asked you to give me 5 non-zero terms. So that'll be 1 minus something squared over 2 factorial plus something to the 4th over 4 factorial minus something to the 6th over 6 factorial plus something to the 8 over 8 factorial. You watch me make sure I don't make any silly errors. And then the thing I'm going to replace all the x's with are x squared. So we get x squared, x squared, x squared, x squared. So if we are looking for an approximation for the function cosine of x squared, it will be what? First 5 terms. So this is a Taylor polynomial of order 16, by the way. Cos of x squared is 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial minus x to the 12th over 6 factorial plus x to the 16th over 8 factorial. We'll make that approximate, right? Because it's a Taylor polynomial of order 16. So that's out there. No doubt about it, that's out there. We want to integrate that from 0 to 1. That was our question on the worksheet. So let me try that. We're going to integrate that crazy function that I have there from 0 to 1 and see what I get. So the integral from 0 to 1 of cos x squared dx is the integral of all that from 0 to 1. Integral from 0 to 1 of 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial minus x to the 12th over 6 factorial plus x to the 16th over 8 factorial dx. Approximately again, because we are just using the first 5 non-zero terms to get there. So you can see this gets pretty complicated. I mean, there's a lot going on here. So let me go ahead and do that. So what is that equal to? X minus x to the 5 over 5 times 2 factorial plus x to the 9th over 9 times 4 factorial minus x to the 13th over 13 times 6 factorial plus x to the 17th over 17 times 8 factorial, evaluated as x goes from 0 to 1. What's nice about that is when x is 0, 0, 0, 0, 0, 0, everything disappears. And 1 to the 5th is 1, 1 to the 9th is 1, 1 to the 13th is 1, 1 to the 17th is 1. Of course, that is 1. So my answer is 1 minus 1 over 5 times 2 factorial plus 1 over 9 times 4 factorial minus 1 over 13 times 6 factorial plus 1 over 17 times 8 factorial. So that's a way for me to approximate that. I'm going to pull out my graphing calculator and see what kind of approximation I get for that. I hope you can see this, at least some of it, although it's not terribly well focused on your screen. But 1 minus 1 over 5 times 2 factorial plus 1 over 9 times 4 factorial minus 1 over 13 times 6 factorial plus 1 over 17 times 8 factorial. Before I hit equals, I'm just going to check to make sure I've loaded everything in correctly. 1 minus 1 over 5 times 2 factorial plus 1 over 9 times 4 factorial minus 1 over 13 times 6 factorial plus 1 over 17 times 8 factorial. And I get 0.9045. So let me write that down on my screen here. So this is approximately 0.9045. Now I will actually ask the computer to do that integral for me, making sure I am in radian mode, which I am. Math, numerical integral from 0 to 1. Whoops. Math, numerical integral, 0, okay. 0 to 1 of cosine of x squared, and then put a parentheses there. Well, I'd like to put a parentheses there if I can. Cos x squared dx, there we go. And what do we get? 9045. Now, how close was that? So 9045, we're good there. What was our previous answer? 90452425, 90452423. Very, very good approximation. So in applied mathematics, you can learn things like how many terms you need to go out to make sure that your answer is within some range. So that's the sort of question we can look at on occasion. All right, so that's a quick look at 2b cos x squared, as well as the integral from 0 to 1 of cos x squared. I also want to look at the inverse tangent function. So that's the next thing I want to examine. I want to examine the Maclaurin series for inverse tangent of x, Taylor series centered at 0, if you will. And then I want to use that to answer a question or two. So, what do we say about that? I've given you a hint. So we're saying f of x is the inverse tangent of x. And what I want to do is I want to figure out some way to express Taylor series for that, centered at 0, to see how that behaves. But I don't want to take all the derivatives. That's going to get nasty. But I have a little advantage I can use. Namely, f prime of x is 1 over 1 plus x squared. That was the hint I had given you on the worksheet. And let's think about this as the form of a naught over 1 minus r. So a naught here over 1 minus r, or first term, right? First term over 1 minus radius. So if that's correct, my first term here is 1. And my radius is negative x squared, right? 1 plus x squared is 1 minus negative x squared. So if that's the case, just to give me the first few terms, that's what I'm interested in. And then we can see if we can write it as a sigma notation. So we get 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th minus dot, dot, dot. So there's 5 non-zero terms. And showing dot, dot, dot as we go to see if there's some way for me to express this in sigma notation. And then I want to use this to answer a question or two. So how do I go from f prime to f? So inverse tangent of x is f of x, which is the integral of f prime of x dx, which is the integral of 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th minus dot, dot, dot dx. So inverse tangent of x. Now, normally speaking, we put the plus c at the end, but this is infinitely long, so I'm not going to be able to put plus c at the end since it never ends. So I'm going to start with the c. Integral of 1 is x, integral of x squared, x cubed over 3, integral of x to the 4th, x to the 5th over 5, integral of x to the 6th, x to the 7th over 7 plus integral of x to the 8th, x to the 9 over 9 minus dot, dot, dot. Now, we know that 0 is the inverse tangent of 0. Tangent of 0 is 0. So that'll be c plus 0 minus 0 plus 0 minus 0 plus 0. So all of that tells me then that c is 0. So that gives me enough to tell you what inverse tangent of x is. That c is 0. I'm able to ignore that successfully. So the inverse tangent of x is x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9 over 9 minus dot, dot, dot. Now I want to express that in sigma form. So it alternates. I'll need a -1 to the k, or -1 to the k plus 1. And I have odd powers. So is there a way for me to go ahead and write that in sigma form for you? Let's see if I can do it. Some odd numbers tend to be 2k plus 1. And I have to start at 0 if that's the case. So 2 times 0 plus 1 is 1, 2 times 1 plus 1 is 3, 2 times 2 plus 1 is 5, 2 times 3 plus 1 is 7, etc. Upstairs, my x is also raised to that 2k plus 1 power. But then I also have a sign flipper. It starts out positive, -1 to the k. Right, -1 to the 0 starts out positive, so I think that's it. So there's my Maclaurin series for inverse tangent of x. Now, I will leave it to you to find the interval of convergence. You would do that with the ratio test and then check endpoints if that's relevant. But again, we've done enough of that. I will leave that to you folks. But here's what I want to do. Here's the question that I would like to try. So this may be a lot to ask, but I'm going to ask you guys to try this, and if you get an answer, post it on the comments. I'll at least give you a minute or so. What I want to look at is I want to use the Taylor series, centered at 0, also known as a Maclaurin series. So use Taylor series for inverse tangent of x to find the limit as x goes to 0 of inverse tangent of x minus x over x cubed. Make sure you can see that. The first few terms should be enough. You've got your Taylor series for inverse tangent up here. Use this version. Don't use the sigma version. That's just going to be confusing. Use this version. Subtract x. You should be able to do that. divide by x cubed. You should be able to do that. And then tell me the limit as x approaches 0 of what's left. Yes, Connor, I'm pretty good with the graphing calculator. So hopefully I can help you guys do that as well. If you want some help with the graphing calculator, come and see me. So work on that problem. If you get an answer, put it on the comments. We'll take a look at it together. If you are in my class, I will be in SEO 430 tomorrow, Wednesday at 3 p.m. I will bring another worksheet like the one I gave you after Monday's lecture to work on in SEO 430. These lectures are nice, but what we're missing is a chance to collaborate on problem solving. So I would like you to come to class if you're able. SEO 430, the building is not being picketed, so you're not crossing a picket line, which I know is important to a lot of people. SEO 430 tomorrow at 3, I'll have a worksheet ready for you to work on that for that hour, and I'll be there to help. If you have any questions on anything else, by all means, find me there too. All right, there is the problem. If you get an answer, please put it in the comments. We'll take a look at it. I'll give you a minute or so to do. Again, hint, take this thing, subtract x, that goes away, and then divide what's left by x cubed, and see if you can find that limit. So go. Can we get someone to give us an answer on the comment sheet? I hope we can. Thanks, Hal. Hal has negative 1/3. And let's see if that is correct. So what do I have? I need to take inverse tangent of x minus x and then divide the result by x cubed. You can see, barely. Inverse tangent to x minus x is x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9 over 9 minus x. So you'll notice if I subtract x, this guy wipes out that guy. Those guys subtract out. So what I'm left with then is I'm left with inverse tangent of x minus x is just negative x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9th over 9 minus an infinite number of other things coming in. And then the next thing I have to do is I've got to divide that by x cubed. So the next line on this argument will be inverse tangent of x minus x all divided by x cubed. So if I divide each one of these pieces by x cubed, sorry, I forgot the cube there. Negative x cubed divided by x cubed is just 1, negative 1/3. X to the 5th divided by x cubed is x squared over 5. X to the 7th divided by x cubed. X to the 4th over 7. X to the 9th divided by x cubed. X to the 6th over 9 minus. The next one will be x to the what? 2, 4, 6. It'll be x to the 8th over something plus x to the 10th over something. The point is, though, as x goes to 0, all of these pieces are going to go to 0. So to finish this off, what we can say is the limit as x goes to 0 of inverse tan x minus x over x cubed as x goes to 0, I get negative 1/3 plus 0 minus 0 plus 0 minus 0 plus 0 minus 0 plus dot, dot, dot equals negative 1/3. which I argue is a lot easier than trying to do this with L'Hopital. Derivative is 3x squared, then 6x, then 6. You've got to take derivatives multiple times to get to L'Hopital. But with the series, it's actually a relatively easy thing for us to do. Okay. The next thing I want to look at is I want to take a look at how we can prove that the derivative of cos x or sine x is cosine x using Maclaurin series. So interestingly enough, I hope this is fair from a mathematics point of view, but prove that the derivative with respect to x of sine x is cos x using Taylor series. Now remember, this is only true if we're working in the world of radians. When I say the derivative of sine is cosine, again, that's only true if the values that we're interested in are indeed radian values. But what is sine x and what is cos x? Well, sine x are the odd powers, so x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial minus dot, dot, dot. You want to memorize the Maclaurin series, Taylor series centered at 0 for sine, cosine, and e to the x. Those are very helpful for us to work with. So let's go ahead and keep that in mind. So knowing that, then, what is the derivative of sine x? What's the derivative of the Maclaurin series? That's the derivative with respect to x of all of this. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9 over 9 factorial minus dot, dot, dot. We take the derivative of each piece. So we get the derivative of sine x is the derivative of x minus the derivative of x cubed over 3 factorial plus the derivative of x to the 5th over 5 factorial minus the derivative of x to the 7th over 7 factorial plus the derivative x to the 9th over 9 factorial plus dot, dot, dot. So what do I get? The derivative of sine x is 1 minus 3x squared over 3 factorial plus 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial plus 9x to the 8th over 9 factorial dot, dot, dot. Interestingly enough, remember 3 factorial is 3, 2, 1. So if I divide out 3, I get 2, 1 or 2 factorial. 5 factorial is 5, 4, 3, 2, 1. If I divide the 5 out, I get 4, 3, 2, 1 or 4 factorial downstairs. So the derivative of sine x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over x factorial. Well, what is that? That, of course, is our series for what? That, of course, is our series for cosine x. So after all of that, we're able to prove then that the derivative of sine x is cosine x. You can kind of see how these things behave. Very nice functions. So the Maclaurin series shows that to us. I'd like to get back to our discussion on inverse tangent, if I could. So we have this Maclaurin series for inverse tangent of x, and I want to use that to figure out a value for pi. So let me make sure that we understand the question that I'm posing. So, I mean, we are looking for a strategy, find a technique that would enable us to approximate pi. Goal. Find a strategy to approximate pi. I don't know. I think this is kind of cool. All I will say is it's a really bad strategy. It doesn't converge very quickly. But, you know, we can do a few terms, and we can see how close we can get. Well, what we showed earlier in our video tonight was that the inverse tangent of x was x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7th plus x to the 9th over 9. So what is the arctangent of 1? That's high praise, mentioning Ramanujan, one of the greatest minds in mathematics. Arctangent of 1 then is 1 minus a third plus a fifth minus a seventh plus a ninth. Do a few more terms maybe. We see the pattern. Minus 11th plus a 13th minus a 15th plus dot, dot, dot. But what do you know? Again, our goal is to find some way to approximate pi. We know that the tangent of pi over 4, tangent of 45 degrees, is sine of 45 over cos of 45, which is 1. Which means the arctangent, the inverse tangent of 1, is pi over 4. So putting all this together, we have this nice long thing that will approximate pi over 4 for us. The inverse tangent of 1 is pi over 4. So pi over 4 should be 1 minus a third plus a fifth minus a seventh plus a ninth minus 11th plus a 13th minus a 15th. And, you know, we could go on forever and ever. And if you're on a desert island and you're bored, I mean, this would be a way that you could develop pi. Again, a really bad way to develop pi. But multiplying both sides by 4, what do we get? Pi is 4 minus 4 thirds plus 4 fifths minus 4 sevenths plus 4 ninths minus 4 elevenths plus 4 thirteenths minus 4 fifteenths plus dot, dot, dot. Now, what will that give us on the graphing calculator? Anything close to pi? You can take a look. I don't know how much of that you can see, but I'm guessing you can see a little bit of it. 4 minus 4 thirds plus 4 fifths minus 4 sevenths plus 4 ninths minus 4 elevenths plus 4 thirteenths minus 4 fifteenths. I'm going to check to make sure what I've put in. And this is supposed to approximate pi. 4 minus 4 thirds plus 4 fifths minus 4 sevenths plus 4 ninths minus 4 elevenths plus 4 thirteenths minus 4 fifteenths. How close is that to pi? 3.017, a very, very bad approximation for pi. But if you want a reasonably good approximation for pi, just to kind of add to your list of things, pi is approximately 355 over 113. My guess is most of you know 22 sevenths. But what is 355 over 113? 3.14159292. And what is pi? 3.1415926. So it's a remarkably good approximation for pi. This will develop all of the decimal places eventually, but it's going to take a ridiculously long time to get there. That's not going to happen very fast for us. All right. If I give you a Maclaurin series, can you figure out what the function is? So this will be our next question to examine. So what if I give you the following? What if I say we are interested in, and I hope this is going to focus for you, the sum as k goes from 0 to infinity of 1 minus 2x to the k over k factorial. So let me leave that there for a minute. I'm going to see if anybody can give me an answer. All right. Abdallah's asking me, come on, focus. You have to focus. There we go. Abdallah's asking me, how is the function pi stored in the calculator? Well, pi's not a function, it's a constant, right? Pi is a constant value. So my guess is that whoever programs the calculator just programs it out to 15 decimal places or whatever it might be. So I doubt that it's using an algorithm to construct pi. I could be wrong, though. I'll look into it and see what I find. So let's see if we can get someone to post an answer. The sum is k goes from 0 to infinity. Connor has an answer for me, and I like what I see. So here's how to do something like this, right? What we're going to say is we're going to say e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus dot, dot, dot. And then writing it in sigma notation, it is the sum as k goes from 0 to infinity of x to the k over k factorial. So looking at this problem, you see that what I have for that is this. That is x, and this is 1 minus 2 to the x. So if this is e to the x, what I have here has to be e to the 1 minus 2x. So that's very good. How about this one? I'm going to give you another problem. I'm going to see if you can evaluate. What if I have pi over 3 minus pi over 3 cubed over 3 factorial plus pi over 3 to the 5th over 5 factorial minus pi over 3 to the 7 over 7 factorial plus dot, dot, dot. See if you can give me that value. What does that equal? This equals what? So again, I will ask you to go ahead and post your answers on the comments, and we'll see what we get for this. All right, How's telling me sine of pi over 3. You have any reinforcement on that one? Do we know what sine of pi over 3 is? Connor's telling me root 3 over 2. Yes, indeed. That's right. So nice work, folks. To remind you of the process there, you want to go ahead and memorize that sine function. So sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. So what we have up there, pi over 3 minus pi over 3 to the cube over 3 factorial plus pi over 3 to the 5th over 5 factorial minus pi over 3 to the 7th over 7 factorial equals sine of pi over 3, which equals root 3 over 2. Let's try another limit question. See if you can do this. What is the limit as x approaches 0 of sine 2x over x? So the steps that you will need to do, let me go ahead and put them in order. Number 1, give me your Taylor series centered at 0 for sine x. That's the first step in the process. The second step in the process is give me a Taylor series for sine 2x. Third step is give me a Taylor series for sine 2x over x. Okay, I'll give you a minute or two to work on that one, and then when you get an answer, please post it on the board, and we'll see where we are. Hopefully, I've convinced you that these Taylor series are certainly helpful for us. They enable us to answer some questions that would be fairly difficult for us to do. What'll be nice about this one, though, is L'Hopital is also pretty easy. So let's go ahead and check it with the Taylor series, and then we'll see if it is the same answer using L'Hopital. So let's see what we get. If you have an answer, please post it in the comments. And I thank all of you who have done that already this evening. How has 2? Let's see if anybody else gets a similar answer. How did you use Taylor series, or did you use L'Hopital? What strategy did you decide to use? Very good. While you're waiting, go ahead and try L'Hopital and see if you get the same answer. All right. Thank you, Kevin. Kevin also has 2. So now that we've had 2 people give me 2, let's go ahead and solve the problem. So the limit as x goes to 0 of sine 2x over x. So you can see the strategy that I laid out for you. Taylor series for sine x is step 1. Sine x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, dot, dot. That's probably good enough for us. We want to have sine of 2x. So wherever I see x, I'm going to replace 2x in parentheses. And we'll see what that's going to look like. So sine of 2x is 2x minus 2x cubed over 3 factorial. 2x cubed over 3 factorial. Plus 2x to the 5th over 5 factorial. Make sure we can see. Plus 2x to the 5th over 5 factorial. Minus 2x to the 7th over 7 factorial. And this goes on forever. So let's go ahead and quickly rewrite sine 2x, simplifying the algebra here for us. So what's that going to give us? Sine 2x is 2x minus 2 cubed is 8. X cubed over 3 factorial plus 2, 4, 8, 16, 32. X to the 5th over 5 factorial minus 2, 4, 8, 16, 32, 64, 128, I think. X to the 7th over 7 factorial. And then remember, we want sine 2x over x. So we've got to divide each one of those things by x. So sine 2x divided by x, 2x divided by x is x minus 8x squared over 3 factorial plus 32x to the 4th over 5 factorial minus 128x to the 6th over 7 factorial plus dot, dot, dot. But you can see the dot, dot, dots just give me higher and higher and higher powers of x. I made a mistake, didn't I? 2x divided by x is 2, not x. And that's kind of important, isn't it? Because that's my answer that we're looking at. So we're going to now take the limit as x goes to 0 of that. So taking the limit on both sides. The limit as x goes to 0 of sine 2x over x is the limit as x goes to 0 of all of this stuff, 2 minus 8x squared over 3 factorial plus 32x to the 4th over 5 factorial minus 128 x to the 6th over 7 factorial plus dot, dot, dot. All of those pieces go to 0. Yes, this piece goes to 0. Ba-boom, this piece goes to 0. This piece goes to 0. Everything after goes to 0. So that my answer is that that limit equals 2. And I thought it might be helpful for us to also try this using L'Hopital to see if we get the same answer. So let us take a look at that. So we're looking at the limit as x goes to 0 of sine 2x over x. Limit as x goes to 0 of sine 2x over x. Let's remember with L'Hopital, you've got to plug things in. Plugging 0 in the top, I get sine 0, which is 0. Plugging 0 on the bottom, I get 0. So L'Hopital is okay. Remember, you can use L'Hopital if you have a 0 over 0 case, or if you have an infinity over infinity case. So what do I do next with L'Hopital? I take the derivative of the top and the derivative of the bottom. limit as x goes to 0, the derivative of sine 2x over the derivative of x, which is the limit as x goes to 0. The derivative of sine 2x is cos 2x times the derivative of 2x, which is 2. The derivative with respect to x of x is 1. Cos of 0 is 1, so that's 2 times 1 over 2, which equals 2. So we've done that problem both ways. So we'll be very happy with that. Well, as long as we're playing with sine, let's finish up today's lesson with one more integral. So let's go ahead and look at the integral from 0 to 0.2 of sine x squared dx. This is another one of those functions that does not have an antiderivative. You cannot integrate sine x squared using any standard procedure, but we can approximate it with this strategy. So, I mean, you should be comfortable with the Maclaurin series for sine x, x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7. I'm just going to choose to stop there because I think I'm going to get pretty good answer just with those values. And if I want to take a look at sine x squared, so approximately, right, that's a 7th order Taylor polynomial for sine x. If I want the sine of x squared, I replace all of the x's with x squared. So the sine of x squared is approximately equal to x squared minus x squared cubed over 3 factorial minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial minus x squared to the 7th over 7 factorial. So you see we have this long, nasty looking problem. What is sine of x squared approximately? X squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial. I want to integrate that from 0 to 0.2, which I think I can do. Integrate from 0 to 0.2. Integrate from 0 to 0.2 of sine of x squared dx is the integral from 0 to 0.2 of all this stuff. X squared minus x to the 6th over 3 factorial. Going to get ugly? You think so? Yeah, maybe. Plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial dx. I just want to see how close we get, right? That's kind of my interest in this problem, which is x cubed over 3 minus x to the 7th over 7 times 3 factorial plus x to the 11th over 11 times 5 factorial minus x to the 15th over 15 times 7 factorial, all from 0 to 0.2. So the zeros disappear. Gone, 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 gone. I'm only going with these first 4 terms. So my final answer will be 0.2 to the 3rd over 3. Okay, that was from the x squared over 3 minus 0.2 to the 7th over 7 times 3 factorial. 0.2 to the 11th over 11 times 5 factorial minus 0.2 to the 15th over 15 times 7 factorial, which I will try to do on my calculator before we run out of time here in 5 minutes. 0.2 to the 3rd over 3 plus minus, actually, minus 0.2 to the 7th over 7 times 3 factorial plus 0.2 to the 11th divided by divided by 11 times 5 factorial. Then I have one more, which I know is basically 0 anyway, but I'll do it. Minus 0.2 to the 15th divided by 15 times 7 factorial. Before I hit enter, I'm going to check my calculator one more time to make sure I've maintained all the signs, because that's a very common mistake to make. 0.2 to the 3rd over 3 minus 0.2 to the 7th over 7 times 3 factorial plus 0.2 to the 11th over 11 times 5 factorial minus 0.2 to the 15th over 15 times 7 factorial. And I get an answer of 0.002666, interesting, 3619. When I actually do it on my calculator, the integral from 0 to 0.2 of sine x squared dx. What do I get? Making sure I am in radian mode, 0 to 0.2 of the sine of x squared dx. I get 0.002666, exactly the same. Wow. So it shows you, just how powerful these Taylor series are. There is no antiderivative for sine x squared. So we certainly could have used the trapezoidal rule. We certainly could have used Simpson's rule to go ahead and do these approximations. And I strongly encourage you to handle that. This is more like a homework problem. Yeah, maybe. I mean, it's a challenging one. So it sounds like you want me to put that thing on your worksheet tomorrow. So just a reminder, if you're in my 3 o'clock class, I hope to see you tomorrow at 3 p.m. in SEO 430. I'll give you a worksheet, a half a dozen problems or so to work on for the hour, so that if you have any questions, I can help you with those. All right, my friends, that's all I have for tonight. Interesting lesson, I hope, and planning on doing this again on Thursday night. So check your email for the information and the streams. Thanks so much.